simple harmonic motion, it is energy conservation in simple harmonic motion. So before starting, these are the upcoming things you need to take care about that. So today's agenda is energy conservation in simple harmonic motion. So let me recap this. So I always recap these things before moving to the new topics. These topics we already learned, so I will explain these things very briefly before moving ahead. And then I ask the brainstorming question to students, whether or not they can distinguish between periodic motion and simple harmonic motion. So I will ask this kind of question and expect participation from students, active involvement of these students. So once I get students actively involving on that, I know the concept, then I will move ahead. So I give these ideas, what is simple harmonic motions, so true and pro-periodic motions in which acceleration is always directed toward the mean position. I can take some example, and I recall them, these things we already discussed in class about displacement of the harmonic motion, their time period, frequency, angular frequency, velocity, and acceleration, these things. Then I ask questions to work in a group, just 5 or 6 minutes, like this question, so that they understood the concept clearly. Then I can show the answer, I can give the feedback to students, and then I start discussing about conservation of energy. Then before going to this conservation of energy concept, I always ask students for their active participation in the class. So I would say that brainstorming question. So I would ask, what is conservation of energy? Because in previous class, in previous chapter, they already know about conservation of energy concept. And once students give idea, just like I'll ask, hello students, can you tell me what is conservation of energy? Yes, I'll give some time, a minute or to think and to share. Then I ask them to think, and then I take the answer and then show my answer. Yes, the conservation of energy means the total energy of isolated system remains constant. Yes, this is correct thing. Yes, so in this conservation of energy, you have the term energy and you have the isolated system. So total energy, you know that total energy in mechanical system, you know that potential energy and kinetic energy. We can say potential energy U, kinetic energy K. So sum of these two energies is called the total energy, and that remains constant in isolated system. Okay. For example, you can use frictionless table or other things where other forces are not acting. The system must be isolated. Okay. We discussed about this thing in previous class. So we are going to apply this conservation of energy concept in context of the simple harmonic motion. So let me take simple example. Let's consider a mass M which is attached to a spring and which is placed on a frictionless table. This table is frictionless because we want to make that conservative force, right? When isolated or the other forces are not acting, the frictionless. That's why consider a mass which is attached to a spring on a frictionless mass and which is oscillating back and forth, right? Hooke's law, according to Hooke's law. And in this case, we know in mechanical energy, the system, the mass has certain position. It will displace something, so it will change the position. So it has certain position and it has motion. So due to the position it has potential energy. Due to the motion it has kinetic energy. So what is the potential energy of the this mass spring system? We know that force is minus kx. If we plot minus F versus x, you will get the straight line which is called the spring constant. We learned about that last time. And if we take the area under this curve, that is the potential energy, which is 1/2 of base and height. So force times x. So in this case we have minus F, right? So in this case this is the height this is minus f, and this is the base, which is x. So we know 1/2 f is equal to minus kx, so minus minus plus, so kx x. So potential energy, so which we call the elastic potential energy in this case, half kx square. If we take example of simple pendulum, this elastic potential energy will be replaced by the gravitational potential energy, right? But this is also potential energy. So potential energy of the mass spring system is half kx square. And what is the kinetic energy of the mass spring system? Which is 1/2 mv square, right? mv square. Okay, so we know the total energy of the system is kinetic energy plus potential energy. So we know the kinetic energy of this mass spring system is half mv square. So we know the half mv is omega square, m omega square. So a square, right? Because this is the angular frequency, angular velocity now, it changed to angular velocity. So a square sine omega square t, because you know the velocity, the velocity formula, because you know the displacement already, a cosine omega t plus phi. So if you take the first derivative of this, that gives the velocity, right? Velocity that becomes minus a omega sine omega t plus phi. We know that omega is the angular frequency, t is the time, phi is phase constant, right? We discussed this in previous class. And what is the potential energy in this case? So that's why 1/2 is 1/2, m is m, and b is simply this term. If you square that one, you will get this whole term. Okay, then potential energy is half kx square. So you know the k, 1/2 k, x is simply the a cosine omega t plus phi. Let's add these two terms. What will happen? If we add these two terms, what we will get? We'll get this, because half k square will be the same term, because m omega square in this case is also k, because spring constant is m omega square. We know that one. So that becomes the potential kinetic energy becomes half m omega square is k, a square sine square omega t plus phi. Potential energy is half k square cosine square omega t plus phi. So these two terms common, then you will have sine omega square t plus phi, cosine square omega t plus phi. So that is the identity, trigonometric identity, that is equal to 1. Then total energy E is equal to half ka square. Okay, so the total energy of the system, E total or E, whatever we can say, that is not going to change. It only depends on the amplitude, how far that particle which is exhibiting simple harmonic motion is displaced from its mean position. It only depends on that maximum position. Okay, maximum displacement, which is called the amplitude. So we can see this not gonna be changed, because amplitude not gonna be changed, maximum displacement not gonna be changed. So the total energy is always constant. So in this case, the last equation is the total mechanical energy of a simple harmonic oscillation, which is constant of the motion and proportional to the square of the amplitude. So you know that. So one important thing I wanted to show you here is you know the total energy E is kinetic energy plus potential energy. If we want to find out the velocity of the particle as a function of the displacement, as a function of the time, as a function of the position, what you would do? So kinetic energy plus potential energy is total energy. We know the total energy is always constant, half k square. Kinetic energy is half mv square, and potential energy is half kx square. So we can write here ka square is equal to mv square plus kx square. So v square is simply, how much v square? We can see v square, mv square is equal to k square minus kx square. So v square is equal to k over m a square minus a square x square. So the velocity, magnitude of velocity can be this, k over m a square minus x square. Okay, now what we know here? So the velocity of the particle exhibiting the simple harmonic motion is simply k over m for the mass spring system or harmonic oscillator, we can say that. So which is equal to a square minus x square. So when x is equal to plus minus a, we can see here what happened. When x is equal to plus minus a to the extreme point from the mean position, when it is oscillating toward and goes to the extreme position, x becomes plus minus a, then velocity becomes 0. Okay, to the left and to the right extreme, the velocity is 0. And maximum displacement, that means it has maximum potential energy. All of the kinetic energy is converted into potential energy at the extreme. But when it return back to toward its mean position, then potential energy start to decrease. And at the mean position, what happened? At the mean position, that means equilibrium position, x becomes 0 and velocity becomes maximum. So at the mean position, total potential energy is converted into the kinetic energy, and total energy is equal to the total energy is equal to the potential energy. Sorry, kinetic energy. So in this way, we can see here. So at the mean position, potential energy is 0, but the kinetic energy is maximum. For the extremum, potential energy is maximum, you see here, but the kinetic energy is minimum. But if you look at the total energy remains constant. Total energy remains constant. Okay, this makes clear that the energy of an oscillator is proportional to the square of the amplitude. It never gonna change. Only the kinetic energy and potential energy is interchanging, is converting from one another, but total energy of the system remains constant. So in this way, we can prove the conservation of energy in simple harmonic motions. So you can see this simple example. So in this figure, you can see how simple harmonic motion can be described as the projections of the motion in uniform circular motion. And you can see here the total energy. This is total energy remains constant always, but only the kinetic energy and potential energy, whether it is gravitational potential energy or elastic potential energy. If it is mass spring system, there is elastic potential energy. If the simple pendulum like situation, there will be the gravitational potential energy, they will change. If potential energy decrease, kinetic energy start to increase. If kinetic energy start to increase, potential energy start to decrease, but their sum would be always equal to the 1/2 k times amplitude square. Okay, this principle is called the principle of conservation of energy. So you can see here, this is the mean position. We can see it has maximum kinetic energy, which is total kinetic energy is equal to total energy here, because potential energy is 0. Okay, but extreme to the left, for example, extreme kinetic energy 0, potential energy maximum, total energy is equal to the total potential energy here. That is 1/2 ka square, right? This is total potential energy here, extreme to the left. So extreme to the right, what is happening? There is also the potential energy maximum. This is the mean. At the mean position, x is 0 position. So here is kinetic energy maximum, potential energy minimum.